going to simulate an AR3 model of length 1024. Hopefully, it is stationary. One can hope. Probably. What? So that is the ACF plot, and we get some peaks here and there. And clearly we can't look at an ACF plot to get the coefficient values. We know that. And there seems to be an oscillatory pattern, yes, which means
it's not right.
no, it has something to do with the roots. Repeating.
Complex.
They're complex. So the roots are possibly complex. I don't know. I'll find out in a bit. But so roots are probably complex. Perhaps there is a system frequency somewhere. It is feasible. So the true model is 0.9, negative 0.65, and 0.1. So I write it on this side over here. And epsilon t is our usual noise. So we can look at the ACF plots. We can also look at the PACF plot. And the PACF plot gives us at 1 we have about 0.5 something. And we have negative 0.5, and this value happens to be 0.1. So the leading coefficient is not being estimated properly by the ACF. This is sort of reasonable, that is reasonable, but that one, not so much.
Two out of 3 years. Still failing.
Okay, so that's our true model, and these are the sample autocorrelations that we got from the ACF plot. We want to estimate the model parameters, which in this case would be phi1, phi2, phi3, because our typical AR3 model is phi1, yt minus 1, phi2, yt minus 2, phi3, yt minus 3 plus epsilon t. Epsilon t is our standard white noise, normally distributed, mean zero, variance sigma squared. And what is a way to estimate the value of phi1, phi2, phi3? Square. Yeah, to find the coefficients. How did we find the coefficients of an AR2?
We did that matrix.
What is it called?
Oh, the Yule-Walker.
The Yule-Walker method. So we could use the Yule-Walker method to change. So in this case, based on the derivation, did I write the matrix
Yeah.
form last time? So it would be 1, row 1, row 2. You can correct me if I'm wrong. 1, row 1, row 1, 1.
Wait, isn't it row one, not one? Like the row one, row two, row three, not one, row one, row two.
One, row one, row two.
Wait, it's not, it's. It's your word. Like it's in the notes I have, it's.
Row naught is always one, actually. So, actually, row one, row two, row three.
I'm not completely crazy.
Row two, this is row two, yes. That would be row one. Row one. Am I right?
Yeah.
So the matrix has to be symmetric, so things just work out. We can extend the derivation in a similar manner for row four. If you go back and look at the matrix for row, excuse me, AR2, it would just be that part, right? AR2 is row one, and the corresponding left-hand side would simply be row one, row two. So we use that part and that part for the AR2 case. Yes? Now, if I go to AR3, what should I do? Just add another column, another row, and that would contain row three in it. And over here, it will end up being row four. So it has a very, what I should say, an iterative or recursive nature to it. So if we put it in matrix form, then computation becomes actually very easy. Let's see. We've got the values of row one, row two, row three. So 0.517, negative 0.111, negative 0.309 would equal 1.517, negative 0.111, 0.517, 1.517, 1, negative 0.111. We all know how to put this in the calculator and evaluate it. So matrix A, matrix B, vector phi. So phi would simply be P inverse A. The matrix is invertible because it's symmetric. And it is going to be plotted there. Okay, so when we invert this, the value of a vector P we have, because we're estimating, happens to be, what are they?
0.827, negative 0.582, and 0.084.
Yes, so the Ewald-Walker method actually did a better job than the PHCF. So typically speaking, the partial autocorrelation plot would help you identify the coefficients easily for, say, an AR1. AR2, pushing it. Anything past that, things would get iffy, which is why we have other methods which rely on simply the autocorrelation to come up with the coefficients. You can see the estimated model using the sample series. It's very close and by all means closer than what the PHCF had. PHCF sort of did a good job with the last two coefficients, but not so great with the first one because its estimate was around 0.5. Good. Now, we want to find a function for the sample autocorrelation. Yes.
Is the PACF usually just completely off for anything greater than AR2?
Typically that's the case. As I mentioned, for AR1, perfect. It will pretty much estimate the value perfectly. AR2 can do. AR3 pushing it. I mean, AR2 is pushing it in some cases. Of course, it always depends on the length of the series also, right? I used a reasonable length, 1024. In practice, if you only had 20 or 24 time points, estimation is going to be okay, won't be the best. Good. So we know how to write the characteristic polynomial. So let's get the characteristic polynomial using the estimate model.
Maybe we can before the windshield wipers just erases everything off.
So the C of Z, all we have to do is move the terms to the other side. We will have YT minus 0.87 L times YT plus 0.582 L times L squared times YT minus 0.084 L cubed YT equals epsilon T. You may ask, well, why should we bother about doing this each and every time? Because remember the psi weights that we had? The psi weights are quite useful because they relate with the noise epsilon T. And when you're trying to make forecasts, epsilon T is going to come into play, which is why we want to find the psi weights. Before I start Armed, I'm going to connect the dots and introduce the concept of a linear filter. So that would also depend on the psi weights. So
you're saying you don't want us to skip directly to these, or
come again?
you don't want us to skip directly to these?
You can, but what I'm trying to say is this characteristic polynomial is important because we will use this to find the psi weights on the other side, right? So that is our phi of Z, the characteristic polynomial. So the next step is to find the roots of the characteristic polynomial. This is a cubic polynomial. How do you find the roots?
Our handy dandy calculator.
Say, we do have complex roots, correct? So that sort of gave us an idea at the very beginning when we looked at the ACF plot. I said there is this oscillatory pattern. It's very likely there is some sort of a system frequency. There is going to be a complex root, which is why when I missed it there, I started questioning myself. There is no way. There has to be a complex root. So anytime you have complex roots, they have to occur in conjugate class. So two roots are complex, one of them is free. Is this a stationary process? The one that we have? Is it causal? Causal.
It's outside the answer.
The roots are all outside the unit circle. You may say, well, the real part is inside, no, the complex part is outside the unit circle. One of them, if it's outside the unit circle, then the root lies outside. So we have causality. Now we have to find lambda 1, lambda 2, and lambda 3. How do we find the first one's easy? Yes. 1 over 5.54, 0.1 something.
181.
0.18, yeah.
How do we find this? So nice. So if you set your calculator in complex mode, easy. Let's say you don't have a calculator, how would you find it? Come in.
Why wouldn't we have our calculators?
Okay, so, mathematically, how would you find lambda c?
Would you rationalize it away?
Very good. We'd rationalize it by multiplying and dividing by the complex conjugate. So, but you guys did it using the calculator, what is it?
0.322 minus 0.69.
So we have lambda 1, lambda 2, and lambda 3. Also, that would give us C1, C2, and C3. C1 is equals C3 are also going to be, excuse me, C1 would be real. C2 and C1 may not be real. We can find C1, C2, C3. How do we find C1?
Isn't it like when the 1 squared?
Lambda 1 squared divided by
When the 1 minus when the 2?
lambda 1 minus lambda 2,
And when the 1 minus when the 3?
lambda 1 minus lambda 3. You guys have the calculator, so use the calculator and tell me what you get. So C1 using the calculator ended up being 0.086. That's expected, real. How do we find C2?
When the 2 squared over when the 2 minus when the 1 times when the 2 minus when the 3.
You all know how to do the magic. C3 would be lambda 3 squared divided by lambda 3 minus lambda 1, lambda 3 minus lambda 2. Now you can see how tedious this process will get when you have series that are, that have more coefficients, which is why we'll try our best to represent a time series with fewer coefficients. But beyond a certain point, you have to rely on computers, which is why programming is quite important. Computation and learning about computation is important in practice. So we have imaginary values, but we tried something last time. We tried to present this in terms of, do we recall? So we can rewrite this in terms of, or the fullest form of multiplied by e raised I theta. And e raised I theta is going to give us the system frequency. So let's see. C1 is easy, 0.086. C2, C3, we can write it as R2, excuse me, R multiplied by e raised I theta, and C3 would be R multiplied by e raised minus I theta. Yes, and we know what the values are. How do we find R? R is the magnitude, so R would be equal to
Square root. Theta 1 square, oh wait, no,
how do you find the magnitude of a complex number?
something squared plus something squared.
Something squared plus something squared. What are the two somethings? Huh? Lambda. How do you find the magnitude of this complex number?
Oh, it's that.
That number's squared.
C.
The entire thing squared? That's squared plus the real part squared plus the imaginary part squared. So 0.456 squared plus 0.43 squared. What do we get? We get 0.627. We can round it to 0.63. Things simple. How about theta?
And the inverse.
This is when Joel was in
Tangent inverse of b over a. We know b is the imaginary part, which is
0.43.
divided by the real part. What do we get? Has to be radians both. So the theta would equal 0.756. What is the system frequency? We had a formula for that. You guys should know this.
2 pi r.
2 pi r,
2 pi theta.
2 pi theta.
Well,
You can look at the notes. So F would be theta divided by 2 pi. System frequency 0.756 divided by 2 pi, which equals
1.19, sorry.
1.19 and 1.19.
That should be 0.12.
Yeah,
Oh, it's the place.
0.12, because that doesn't make sense. New denominator is bigger. So if f is 0.12, what is t? T is the period. What is the period?
Frequency.
1 over 0.12, which is
Inverse of
inverse of that, which is
that. 8.33.
8.33. We'll call it approximately 8. What is the significance of that value? So look at this picture and tell me what is the significance of that t. We've been over this before.
Is that the relevant period?
It is the approximate period at which things cycle, right? 1, 2, 3, 4, 5, 6, approximately 7.
Yeah.
You know, for one full period. So that's the period of oscillation that we see.
So does that mean, does that mean our values are gonna fall below that line of relevance at 8? Does that mean that the values that exceed the line of relevance, is that an 8? Because
Yeah, it's probably 7 or 8. That's when it'll, you know, go up. So there is an underlying period of 8.
That's not right. Underlying POV.
Now that we have C1, C2, C3, we have the system frequency and all, what was our next step? Or we have to find the psi weight, right? And we have that general expression for it. What is that general expression? In this case, the roots are all distinct. So I could write C1 lambda 1 raised j plus C2 lambda 2 raised j plus C3 lambda 3 raised j. Yes? C1 is 0.086 multiplied by what do we get? What did we get for lambda 1? 0.181 raised j. And C2, let's express it in the form of multiplied by e raised I theta. So R would end up being 0.63. E raised I, I'll call it 0.76, rounded to 2 decimals. What is lambda 2?
0.322 minus 0.69.
0.322 minus 0.69.
Yep.
I've rounded to 0.32. It is best if I could write that in the form as well. Do you agree? It'll make things easier for us. So let's go ahead and express this in the polar form R multiplied by e raised I theta for lambda 2 and lambda 3. We plugged in the size, excuse me, C1, C2, C3, wrote it in the polar form, and then we got the Euler form, and then lambda, we did the same thing, converted to R e raised I theta, plugged it in here, did all kinds of simplifications in the algebra, and then we came to the very last step, and it's got complex I in it. We need a real number, correct? We can't have a complex value because they're imaginary, just like our friends.
Just like Alice's too.
I didn't hear this.
Just like Alex's.
Yeah. It was a neat joke, I'm sorry.
I believe it's got more than me.
I go, it was there for the taking.
More than that. So psi j would be 0.086 times 0.181j. And you may think, oh, this looks awful, and that is not going to work because we have a complex value. But recall, e raised I theta plus e raised minus I theta divided by 2.
That geometry.
Aren't you not two of you are math based, right? You have done this before.
In what kind of class? In what class?
It's not big complex analysis. Or pre-calculus.
Actually, I skipped that one.
That was a few semesters
We
ago.
have done this in differential ways.
That's next semester.
Definitely. So,
So that was 16 when I took the
oh, e raised I theta plus e raised minus I theta divided by 2 is cosine theta. So I'll have e raised I theta plus e raised minus I theta equals 2 cosine theta. So if you observe carefully, you keep in mind that this J is not a complex notation. Some textbooks use J for a complex number. In our case, we're using I for the complex number notation, and that J comes from the power of lambda. So if you look at our derivation, which one might so if I pull I out, I would have minus 0.76 minus 0.76. I could have done it the other way also. It's really dumb math though, because cosine is a what function? It's an even function.
Well, there's a lot of things you could have gone with, the cosine is a lot.
If I pull I out, I would have minus 0.76 plus 1.08 J. If I pull a minus I out, I would have minus 0.76 plus 1.08 J. Yes? So that would be my theta, right? So they match up, so I can plug it in there. So the last two terms would simply reduce to plus 0.63 times 0.68 raised J multiplied by 2 cosine minus 0.76 plus 1.08 J. Yes? As I said, cosine is an even function. I could have done it the other way around. The answer would still be the same. So our final expression for sideways is 0.08, 0.181 raised J plus 0.63 times 0.68 raised J. Let me multiply by 2. So 2 times 0.63, 1.26. Yes. And 0.68 raised J cosine that is my final answer. And I got rid of all complex numbers. Yes. So sure, we had a formula for the AR2 case, but we can't always rely on that formula because for AR3, we have to do this, AR4, similar process. So if I plug in J equals 0, I will end up having 0.08. J is 0 there. 1.26 times cosine negative 0.76 plus 0. And what do we get? Let's make something nice. So the answer is 0.993. So do we have faith in our calculation? Yes, because the psi naught value must always be 1. Here it is close to 1 because not exactly 1. It's estimate and we rounded a whole bunch of stuff as we went along. So it is close to 1, so we are onto this great. So we can find the other side weight, side 2, side 3, just by changing the values J. So the series YT can now be expressed in terms of side weights, purely side weights and the noise. Why are the side weights important? Next time, which is next Tuesday, I will start with a linear filter that would purely depend on side weights and the noise terms. Another thing I've got to mention, this process that we used can also be applied for the AR2 case with complex roots. We won't have that. And if it is an AR2, and if it has complex roots, C1, C2 must be conjugates. Lambda 1, lambda 2 must be conjugates. You do this process, at the end of the day, you end up with an expression of that sort. And the periodicity in the ACF comes from the cosine.